Let's take a look at some statistics that we call directly. In this plot of the iris dataset, sepal length is described by species. What can we do with this data? A typical way to summarize this data would be to take the mean and standard deviation, or the 95% confidence interval. We can calculate these values manually, or we can do it directly in ggplot2. Let's see how it works. The function smean-dot-sdl from the Hmisc package returns the mean plus or minus one standard deviation as a named vector. By setting the mult argument to 1, we specify one standard deviation. In ggplot2, the mean_sdl converts this vector to a data frame, renaming the variables to match ggplot2 aesthetics. We call mean_sdl using the fun.data argument of the stat summary function. By default, we get geom point range, which requires y, ymin, and ymax, exactly what is returned by mean_sdl. For error bars, we can just calculate the mean and use point as a geom. Then we can call mean_sdl using the error bar geom, where we can also set the width of the error bars. But notice that we could have also made a typical bar plot with error bars by simply calling the bar geom. But this is not recommended. We'll learn why when we get to DataVis best practices later on. The 95% confidence interval is also straightforward. Mean CL normal returns the mean and the upper and lower bounds of the 95% confidence interval, calculated using the t-distribution. Two other useful stat layer functions are stat function and stat QQ. These are particularly useful if you want to look at distributions. Statisticians typically use visual cues to get an idea about the distribution of their data instead of relying on numbers. To see this in action, let's return to the first example we used in the first course. The mammalian body and brain weights stored in the mammal's data frame. We mentioned that our linear model fitted the log10 transform data reasonably well. What we mean is that the log transform data appears to be normally distributed. So let's take a look at that in detail. For a stat function, we can specify any function and produce a theoretical probability distribution as a line. Here we'll call a normal distribution, that's dnorm, and add arguments as a list to center it on our distribution. That's the mean and the SD. This allows us to compare how well our data is normally distributed. The log10 mammalian body weight is described by a log normal curve very well. Notice that we have another geom here, geom rug, which has those little tick marks on the bottom of the plot. This is a handy way of seeing the actual values in combination with a summary distribution. An empirical density plot would be a nice alternative to the histogram, but we'll get to that in the next course. QQ plots also allow us to compare our data to a distribution. In this case, we plot our sample against a theoretical distribution, like the normal, and draw a line intersecting the scatter plot at the first and third quartiles. The closer that our data aligns to this line, the more closely it matches the theoretical distribution in question. There are more stat functions which are available for you to explore during the exercises.